Hey, everybody. I'm a little bit late. It is 3 minutes behind. I'm just posting the link to Google Classroom, so no one's gotten linked yet. But maybe some of you found my channel. We'll see. And I know it's a blank screen. As soon as I get the link up, then I'll put my iPad up. Everything's working a tad slow right now. Okay. So okay. Loading Google Classroom. Getting to post the link. Okay, now it's posted on Google Classroom, so at least people get started. Now we're only 7 minutes late. And I don't see anyone here yet, probably because I just posted a link. But now I can pull up my iPad. Great. Okay. Now we're sharing. We've got one person here. We're in business. Okay. Who's here? Can you hear me? The sound all right? Steven's here. And Shiva's here. And Steven can even hear me. Okay. That's great. But can you see my screen? You can see the screen? Okay, so maybe I just can't see it on my end. Everything's perfect. Cool. Okay. Pre-calc. Review. Unit 7. And there it is. Now I can see everything. Great. And let's see. I was thinking I would go through that practice sheet. Some of each type of the problems that I mentioned would be corresponding to each of the standards. At least one of each kind, which should go pretty quick. And then afterwards, if you have more questions, I can go over those. So, if there's anything you don't understand, of course, stop me. And if there's anything I need to spend more time on, let me know. Hey, Xander, how's it going? And we're now 12 minutes in. Sorry about that late start. And I am going to start talking about polynomial functions and their graphs, which is our first core standards. And I'm going to do one from page 241. And I'm going to look at number 17. And this is a core standard. And number 17 looks like we are supposed to graph f of x equals x minus 1 squared times x plus 3 times x plus 1. And I want you to be able to sketch a rough graph of the function that shows the zeros and be able to state domain and range, maybe end behavior. Okay, so I have zeros at x equals -3, -1, and +1. So I'm going to say -1, -2, -3, +1, 2, 3. And 1, 2, 3, and actually, I'm not even going to give a scale on the y-axis. Who needs it? So there's a 0 at -3, a 0 at -1, and a 0 at 1. I'm noticing that this function, it would have an x squared times an x times an x. So overall, the end behavior is like the graph of x to the 4th. Let's write that down. End behavior is x squared times x times x. So that's x to the 4th. So that means the end behavior in general looks like that. As x goes to -infinity, y goes to infinity, and as x goes towards infinity, y also goes towards infinity. So as I'm graphing, I'm saying it's coming down from infinity. Then I'm coming over here and noticing that this 0, which happens at x equals -3, has odd multiplicity because this is to the 1st power. So the function must cross the x-axis, change sign from positive to negative at -3. Then my next 0 is at -1. Again, odd multiplicity. So the function's going to go back up. Now it seems like it would be nice to figure out what the y-intercept is. So the y-intercept I would get by multiplying, let's see, -1 squared is 1, times 3 is 3, times 1 is 3. So let's give myself the y-axis values, 1, 2, 3, and 3. Here we go. Up to 3, and then down because I have a 0 at 1. And I know that at 1, the function should bounce. And go back up. Positive. Cool. Obviously, I know that's a minimum because of the function terms. I don't really know where the minimum is here. I don't really know where the maximum is here. That's not something I would expect you to be able to do without a graphing calculator. However, making a rough sketch that shows where the graph is positive and negative and positive and positive and where the zeros are is something I expect you to be able to do on this core standard question without a graphing calculator. Let's see. We wrote about the end behavior. You should be able to look at a function and analyze end behavior. We wrote about the zeros. You should be able to find zeros. The domain is all real numbers. And the range here, I would not be able to expect you to find the range without a graphing calculator. So the range here, I'm going to say there's some minimum point. Let's call it C. I don't know what it is, but there's obviously a minimum point. It's obviously below 0. It's some value, C. And I would expect you to be able to find it with calculus, but I would not expect you to be able to find it at the pre-calculus stage without a graphing utility. Lindy says, why does it bounce again? Oh, so the graph bounces right here, does not change sign, goes from positive to positive because the 0 that forms this 0 at 1 was right here and it had even multiplicity. So you can think about it being like a little tiny miniature x squared graph, right? This is what y equals x squared would look like. We have a little x squared graph right there. It's going to go positive to positive. I did not mean to do that. Let me see. Erase. Just, oh, lost it. There we go. Did I answer your question, Lindy? Hopefully. Yep, good. Cool. So odd multiplicity, that's odd multiplicity. Oh, that's odd multiplicity, crosses. Odd multiplicity, crosses. So here we had odd multiplicity. And here we had odd multiplicity, but here we have even multiplicity. Even, odd, odd. Okay. I'm doing this review session at school because my wife was having friends over, and now the fire alarm is ringing. Okay, it stopped. Hopefully I don't need to evacuate. I'm going to keep doing math. Anyway. Odd, odd, even, odd, crosses, even, bounces. Odd number 1, even number 2. Yes, fire. Thank you, Xander. I appreciate the warning. Domain was all reals. Range is obviously limited over some value greater than C. I don't know what C is, but we could just mark it that there's some number C here, abouts. Oh, now there's an announcement. Mr. Z says it's a false alarm. I'm safe. I do not need to evacuate. I'm not. I am very safe. I'm all safe. I'm glad you were worried. I appreciate any concern you may have had, but Mr. Z just came on the announcement and says I'm safe. Great. Okay, back to math. That was number 17. That is all that I would expect you to be able to do. Find zeros, find end behavior, find domain and range, graph a function, show where it's positive, negative, positive, and here positive. Yes, Lindy, I believe Mr. Z is still there, considering he just came on the loudspeaker and made an announcement. So Mr. Z and myself are both hanging out at Pioneer at 7:20 on us tonight. Any questions about this core standard question, being able to graph polynomial functions by hand in simple cases, identifying zeros, and showing end behavior? Seeing no questions, I'm going to move on to our second of 2 core standards, graphing rational functions. So now I'm on page 241, number 33. I am again doing a core standard problem, this time on rational functions, and it's graph g of x equal to x squared minus 4 over x squared minus x minus 2. Okay. So I'm going to go ahead and factor to begin with. So I'm going to write down here that g of x could be rewritten. Factoring x squared is minus 4, I get x minus 2, x plus 2. Factoring x squared minus x minus 2, I get x minus 2, x plus 1. I picked this one because I like it because we get all of the different features. We're going to have a whole, we're going to have a 0, and we're going to have an asymptote. How much fun. So there's a 0 that's just in the numerator. So there's a 0 at x equals negative 2. There's an asymptote because there's a 0 in the denominator at x equals negative 1. And there's a whole because you have a factor that's in both the numerator and the denominator at x equals 2. Dope. Okay. I am sketching a graph. I'm going to need an x-axis and a y-axis. I've got 1, 2, 3, 4, negative 1, negative 2, negative 3, negative 4, 1, 2, 3, 4, negative 1, negative 2, negative 3, negative 4. Okay. Let's see. I can tell that this function is going to be asymptotic with respect to y equals 1. So there's n behavior and behavior as x goes towards negative infinity. Let's start with y is going to go towards 1. As x goes to positive infinity, y goes to 1. So here's my horizontal asymptote at y equals 1. And here's my vertical asymptote at x equals negative 1. Sweet. Okay, now I'm going to plug in 0 to kind of get a sense of where the y-intercept is. So I got 0 minus 4 is negative 4. 0 minus 2 is negative 2. So negative 4 divided by negative 2 is 2. So I have a point here at 0, 2. G of 0 equaled 2. So that meant I have a y-intercept at 0, 2. All right. Then let's say I know I have a 0 at negative 2, 0. When you plug in negative 2, you will get a 0. And then I know that 0 has odd multiplicity, so the graph should cross there. I know I have an asymptote at y equals 1, so I've got to go that way. And got to come down that way. And then I know at this asymptote, the graph should change sign. So I've got to be coming this way and this way. Bam. There we go. So let's see. I knew I had a point here because there was a 0 at negative 2, 0. I knew that the n behavior was going to head towards 1. So I had to be going off that way. I knew that the graph couldn't cross back to negative, obviously, because there's no more zeros. I knew that the graph had to be headed down this way towards this asymptote. because it couldn't cross back to positive because there's no more zeros. And I knew that then at this asymptote, because we had odd multiplicity, that the graph needed to change sign. So it went from negative to positive. So it has to be coming up here. I know when I plug in 0, I get 2. So I've got 0, 2. And then it needs to be approaching y equals 1 as I go towards positive infinity. So I got to be headed towards that asymptote. The only thing I'm missing now is that I know I have a hole at x equals 2. So I'm going to erase a little bit of graph to give myself a hole at x equals 2. Hole. I could go ahead and find out what the value of that point is by plugging in 2 without the x minus 2. So if I plugged in 2 to g of x, if I went ahead and simplified, cancel, cancel, and found this new function that was simplified, g sub 1 of x, and it was x plus 2 over x plus 1, where I've reduced common terms, and I plugged 2 into that function, I would have g sub 1 of 2 equals 4 over 3. So that point must be at 2, 4 thirds, which looks pretty good. Yeah, 1 1/3, right about there. Cool. Domain. Domain is going to be the set of values x such that x does not equal -1, nor can x equal +2. And the range is going to be the set of values y such that y does not equal 1. We're going to approach 1, but never equal it. And y never equals 4 thirds. Because there's a hole in the graph at 2, 4 thirds. Okay. I expect you to be able to find zeros, asymptotes, holes. I expect you to be able to analyze simple rational functions and determine end behavior. I expect you to be able to look at graphs and determine domain and range, and sketch basic graphs of rational functions based on that analysis. Any questions about our second core standard, graphing simple rational functions? Okay, seeing no questions, I'm going to go ahead and move on to some extended standards. Like using the remainder theorem with long division. So 45 through 48. Find the remainder. Great. So we're going to do some long division. Let's try page, let's go back to black, page 241, and we're going to check out number 47. And it's an extended standard now. Okay, and f of x equals x to the fourth minus 2x cubed plus 15x minus 2. G of x equals x plus 2. And they're saying find the remainder r if f of x is divided by g of x. Cool. So a little long division practice. X plus 2 into x to the fourth minus 2x cubed plus 15x minus 2. X goes into x to the fourth, x cubed times. X cubed times x is x to the fourth. X cubed times 2 is 2x cubed. X to the fourth minus x to the fourth is 0. Negative 2x cubed minus 2x cubed is negative 4x cubed. X goes into negative 4x cubed, negative 4x squared times. Negative 4x squared. Oh, I forgot to bring down the 15x. Negative 4x squared times x is negative 4x cubed. Negative 4x squared times 2 is negative 8x squared. Negative 4x cubed minus negative 4x cubed is 0. 15x minus negative 8x squared. Well, I have no 8x squareds. I have no x squareds to add to. So minus negative 8x squared is positive 8x squared. And I can again bring down the 15x. X goes into 8x squared 8x times. Eight x times x is 8x squared. And 8x times 2 is 16x. Eight x squared minus 8x squared is 0. 15x minus 16x is negative x. X goes into negative x negative 1 times. Negative 1 times x is negative x. Negative 1 times 2 is minus 2. We forgot to bring down that negative 2. Then subtract 0, 0 plus 0 over x plus 2. So the remainder is 0. And g of x is a factor of f of x. So we just found that we could write f of x in a further factored form of f of x equals x plus 2 times x cubed minus 4x squared plus 8x minus 1. That would be a strategy for factoring f of x. Lorenzo would like to reiterate that you are not allowed notes on a unit exam. You're only allowed notes when there are multiple units at stake. So midterms, and final exams, not unit exams. I expect you should be able to maintain a knowledge of a single unit in your head. So thank you for clarifying, Lorenzo. Correct. No notes. Cool. So that was an extended standard, knowing and applying the remainder theorem via long division. Okay, and then I'm going to do another long division problem because we had another standard that had to do with long division, which was, can you apply long division to rewrite simple rational expressions in different forms? So another one, same problem set in the book, but a different standard it's applied to, is we're going to divide, we're going to rewrite. So I'm doing page 241, number 46. And the same skill as long division. And it's an extended standard. And here I am rewriting this rational expression, 2x cubed plus 8x squared minus 5x plus 5 over x minus 2 to show end behavior. Okay, so again, I am applying long division, x minus 2 into 2x cubed plus 8x squared minus 5x plus 5. X goes into 2x cubed, 2x squared times. 2x squared times x is 2x cubed. 2x squared times negative 2 is negative 4x squared. Subtract 2x cubed minus 2x cubed is 0. 8x squared minus negative 4x squared is the same as 8x squared plus 4x squared, which is 12x squared. X goes into 12x squared 12x times. 12x times x is 12x squared. 12x times negative 2 is negative 24x. Bring down the 5x. Subtract. Negative 5x plus 24x makes 19x. I can go ahead and bring down the 5 now. X goes into 19x 19 times. 19 times x is 19x. 19 times negative 2 is negative 38 minus 0. 5 plus 38 is 43 plus 43 over x minus 2. Cool. I think I did that all right. 2x cubed, 8x squared minus 5x, 5. x, 2x cubed, 2x squared, 2x cubed, minus, plus 12. Yep. Looks good to me. Okay. So this shows us that the end behavior of two x cubed plus 8x squared minus 5x plus 5 over x minus 2 is the same as y equals 2x squared. And we could see what I mean by that by pulling in Desmos and saying, let's check out the graph of 2x cubed over minus 2, and it's 2x cubed plus 8x squared minus 5x plus 5. So there's pretty crazy looking rational function. But all in all, the end behavior is just, let's check my division. Another way of writing that same function, I'm rewriting it in another form, which helps me clarify the end behavior, which is 2x squared plus 12x. Sorry, I got a phone call. 12x plus 19 plus 43 over x minus 2. And yes, I did it. I found a perfect identity. And in the end, that's all just like 2x squared. We back out and look at the end behavior. Yeah, basically what this graph is doing in the big picture is just like the graph of y equals 2x squared. Cool. So in the small term, zoomed in, it doesn't really look like it, but when we zoom out, it's just y equals 2x squared. Cool. Some things to maybe notice about this graph. You can see it has that 0 at negative 4.653. So it's not the kind of thing I would make you factor. And it's got its vertical asymptote at x equals 2. I'm going to check that phone call and make sure it wasn't anything important. Right, nothing important. Okay, so that was another extended standard involving long division about rewriting rational expressions in different forms, like using long division. Okay, another extended standards is on solving equations and inequalities. So let's look at another problem where we're going to solve an inequality. So number page 241, and I'm now checking out, let's check out 39. Rational inequality. And this is another extended standard. And this one says solve 2x minus 6 over 1 minus x less than 2. Cool. So step 1 of our process said we should need to set this equal to 0. So minus 2 minus 2. Two x minus 6 over 1 minus x minus 2 is less than 0. Okay, now I'd like a common denominator. So I've got 2x minus 6 over 1 minus x, and I'm going to times that by 2. Oh no, that's all good. But then minus 2 times 1 minus x over 1 minus x less than 0. So here I took the value of 2 and gave it the common denominator. Let me look at the standards, Xander. I'm pausing now. So, Xander, it is possible that I would give you a problem like that when I'm asking you to extend polynomial identities to the complex numbers, that you can do arithmetic on complex numbers. So yes, it is possible that I would give you a question where you had to find a particular polynomial equation given particular zeros, probably involving complex zeros. And I would do a problem like that if you wanted me to, Xander, as soon as I've done with the ones I'm already planning on doing. So let's see. I now have my common denominator. Let's adjust a little bit. 1 minus x minus, let's see, 2 minus 2x. And 2x minus negative 2x is 4x. Minus 6 minus 2 is minus 8. Okay, and now that I've arranged everything nicely, I can say that looking at this function, it's got a 0. Oh, let's factor it, sorry. 4 times x minus 2 over 1 minus x less than 0. So it's got a 0 at x equals 2 and an asymptote at x equals 1. And I'm going to make my number line. And I'm going to say, okay, here's 1 and here's 2. I'm going to go ahead and plug in 0 to start with, because 0 is a nice, easy thing to plug in. 0 minus 6 over 1, that is clearly less than 2. Same thing over here. 0, negative 8 over 1, clearly less than 0. So in this section, when I plug in 0, I get a negative value. Between 1 and 2, I'm going to bet that because we have an asymptote at x equals 1, it should change value because that asymptote has odd multiplicity. So we're going to switch to a positive value. And then at 2, we change values again after that 0, so it's going to be a negative value. If I plugged in 1.5, let's see, 1.5, we'd have 6 minus 8 is negative 2 over a negative, yep, so we would have a, 6 minus 8 is negative 2. 1 minus 1.5 is negative 0.5, so we'd have negative over negative, which is positive. And over here, if we plugged in a test value of 3, we'd get 12, so positive on the top, negative on the bottom, negative. So the question is asking where is the value negative, and the answer is for negative infinity to 1, union 2 to infinity. Great. Extended standard, looking at solving rational inequalities. Okay. The last ones I was asking about was on the fundamental theorem of algebra and complex zeros. Oh no, so 75 to 78 is about complex zeros. Ooh, cool. Okay, yeah, so I was going to do one of these anyway, Xander. I'm on it. Okay, so now I'm looking at page 242, and I'm looking at number 75. And this is another extended standard. And the problem says, well, let's take a picture of this one. Okay, so in 75 through 78, information is given about a complex polynomial f of x with real coefficients. Find the remaining zeros of f, then find a polynomial with real coefficients that has the same zeros. Okay, so this is a third degree polynomial, so it can only have 3 total zeros. It has a 0 at 4 plus I and at 6. I happen to know that I need to, let's pull this one out. This is 75. There we go. We know that we need to find the missing 0. That's the conjugate pair to 4 plus I, because in the end, we're going to have real number coefficients. So the remaining 0 needs to be 4 minus. Oh. The remaining 0 was 4 minus I. Okay, so sorry, I sneezed. Pause there. Thank you, Xander. Thank you, Lindy. Much appreciated. 4 minus I. So that's the remaining 0. Because it's the conjugate pair with 4 plus I, and that's the only way that we multiply and get the i's to cancel out, so that in the end we get real numbers. Okay, so now I've got all my zeros, so I must have factors of x minus 4 plus I, another factor of x minus 6, and another factor of x minus 4 minus I. So here, This one went there, and this one went there, and this one went there. So that becomes x minus 4 minus I times x minus 6 times x minus 4 plus I. I'm going to go ahead and switch the order just to do the pieces with the i's first. Okay. And now I'm just distributing. X times x is x squared. X times negative 4 is minus 4x. X times I is x I. Negative 4 times x is minus 4x. Negative 4 times negative 4 is plus 16. Negative 4 times I is minus 4I. And negative I times x is minus ix. Negative I times negative 4 is plus 4I. And negative I times I is minus I squared. Okay. A little bit of canceling to be done. I have a minus 4x and a minus 4x, but I have a plus xi and a minus xi. I have a minus 4i and a plus 4i. So I've got a x squared. The minus 4x and the minus 4x become plus 8x plus 16. So I got that. I got those. I got that. Minus I squared. Well, I squared is negative 1. Minus negative 1 is plus 1. Sweet. Times x minus 6. So my real number polynomial that has real coefficients is x squared plus 8x plus 17 times x minus 6. Sweet. There's my answer. So I think that was the kind of question that Xander was asking about. It is an extended standard, drawing on the fundamental theorem of algebra and the nature of complex zeros. And there was the practice for it. Oh, and we were also thinking about extending polynomial identities over the complex numbers. Cool. So the last one, we're practicing the fundamental theorem of algebra, and we're finding complex zeros given the polynomial function. So last problem I'm going to do is another extended standard practice. I'm going to do page 242, number 83, and it is again an extended standard on applying the fundamental theorem of algebra. So we're at f of x. Oh, shoot. Just a sec. F of x equals x to the fourth minus 4x cubed plus 9x squared minus 20x plus 20. And the first step on these is to look at the graph and check out the real zeros. So again, this is a core standards problem. So you can expect to be able to use a graphing, sorry, not a core standard problem, an extended standard problem. So you can expect to be able to use a graphing calculator. X to the fourth minus 4x cubed plus 9x squared minus 20x plus 20. Okay, so we have only one real zero, it appears. When you plug in 2, you get 0. Okay, so we're going to have 3 more non-real zeros. How's that going to work? X to the... Oh, this one's got even multiplicity. So this guy, there must be even multiplicity at x minus 2 because the graph bounces. So there are 2 zeros at x equals 2. So we must have x minus 2 squared must be a factor of this function. Ooh, so we're going to do a great long division problem. So x minus 2 squared becomes x squared minus 4x plus 4. And we need to divide x squared minus 4x plus 4 into x to the fourth minus 4x cubed plus 9x squared minus 20x plus 20. Now this is going to be fun. Let's move that out of the way. X squared goes into the x to the fourth, x squared times. X squared times x squared is x to the fourth. X squared times negative 4x is negative 4x cubed. X squared times 4 is 4x squared. Subtract. X to the fourth minus x to the fourth is 0. Negative 4x cubed minus negative 4x cubed is 0. 9x squared minus 4x squared is 5x squared. Bring down. X squared goes into 5x squared 5 times plus 5. I'm going to bring down this as well while I'm at it. Plus 5 is 5x squared minus 20x plus 20. Subtract 0, 0, 0. So I have just found that I could factor f of x, and it became x minus 2 squared times x squared plus 5. So there were 2 real zeros at 2. X equals 2 is a 0, and that had even multiplicity. And then we're going to have 2 imaginary zeros from the factor x squared plus 5. So what happens when x squared plus 5 equals 0? Well, x squared would need to equal negative 5. So x equals plus or minus the square root of negative 5. So x equals plus or minus square root of 5i. So this one has x equals root 5i and x equals negative root 5i. So here we can do kind of another fun thing and check first our division, and then we can even think about our complex zeros. So we can say we originally started with x to the fourth. Go home. X to the fourth minus 4x to the third plus 9x squared minus 20x plus 20. There was the entire graph with the 1 0 at 2. Well, 2 zeros at 2. It had even multiplicity. And now we adjusted it, and we realized that when we factored, it could be x minus 2 squared times x squared plus 5. And we can show that that's identity. The graphs are exactly the same. And we can show that we can make it x minus 2, another 0 at x minus 2, a 0 at x minus square root of 5 I. Oh, it doesn't let me use an unreal number in this. That's very sad. Moderately disappointed in that. X equals, x plus square root of 5 I. And can I set I equal to the square root of negative 1? Hey, does it let me? Then it lets me. Sweet. So then we have, oh, but it doesn't graph the blue function. So it can't graph complex numbers in Desmos. I thought it could. Too bad. Anyway, that's what should be the same identity as x minus 2 squared times x squared plus 5. But you can't check because Desmos can't handle imaginary numbers. But there we go. Any questions on that last extended standard problem? Okay. Only a couple of you were watching live. Didn't have a ton of questions today, but hopefully you do get all of tomorrow with your day off to go over this and study for your exam on Friday. There'll be a core standards question with no graphing calculators, and then an extended standards question where you do have access to graphing calculators. Sorry, extended standards questions, another part. If you've already met the core standards, you don't need to do them again. If you haven't yet, you're going to want to do that. You need to meet the core standards to get a C. You want to do the extended standards to get an A or a B. Seeing no further questions about any of it or anything else that you need me to practice, I'm going to go ahead and say good night. I'll see you all on Friday. Hope this is helpful.